All right. All right, well, thank you very much for coming tonight. I'm going to go ahead and try to just project and not use a microphone, but if at any point you can't hear me, just give a little wave and we'll pull the old microphone out, okay? All right, so tonight I'm going to talk about people in technology. Can't we all just get along? Seems like in 2019 we should be able to, but it's actually a really, really difficult thing to do. So let's see, here we go. So I want to start, query the crowd here. What do you think of when you hear the word technology? Just blurt it out. Phones, computers, tools, chips, robots, drones. Right? Many of you said these kinds of things. Anything that helps society or relieves work. Right? Whenever we hear the word technology, inevitably, our mind goes to devices. We think of things. Right? But the reality is that technology doesn't really exist without people. And people are the consumers and the users of technology. And that relationship is really important because the success of a technology depends on how much we like it, right? And technology, the human technology gap, the human technology divide is becoming smaller and smaller as technologies get better and better and as we learn to adapt to them. Right? So it starts out with us just using devices. We use computers, we use phones, we use tablets, right? But technologies, very smart technologies, are coming into all facets of life. This is the current Amazon warehouse where there's robots moving around all over the place, working together with humans to get things where they need to be. Right? This little video, we won't watch the whole thing, but we'll just watch a little bit. This is a surgical robot that's on the market called Da Vinci. Has anyone ever heard of the Da Vinci? So this is a surgical robot where the surgeon's controlling the arms of the robot, but from a separate console. Right? So I'll just show you a little clip. There's nothing gross in here. Let's move it up to right about here. Right? So the surgeon's sitting at the console moving the little appendages and the robotic arms are doing all of the work. And we can go even further. Right? There's technologies. Has anyone heard of a telerobot? I'm going to talk a little bit more about telerobots later in the talk. But these are essentially platforms where a person sits at a computer and controls a robot in another location, and your face shows up on the robot. Right? So the idea is you can be present in some form in a location where you physically aren't there. Right? So now we're looking at technologies where we're trying to embody ourselves, or at least some form of ourselves, when we're not really there. And we even have technologies that connect directly with us and are controlled by our minds. So in this video, about 20 seconds, we're going to watch a gentleman play the piano with a prosthetic arm that's controlled by his mind. The people and technology horizon's here, right? And I think this image kind of shows what's happening. This divide, this how we interact together and how we work with technology is becoming smaller and smaller. And so much so that we're adapting to technologies in new ways. Kids can pick up touchscreens and just know what to do, right? Mine do it all the time, and I'm like, how did you get here, right? And technologies can learn from us. There's machine learning and AI. They can learn from us how to do things that we've never taught them. But how do people and technology get along? Right? A lot of times we think of things like this, right? Like you just really want to throw that thing out the window, right? It is such a struggle to see like something so simple, right? But imagine if that's how it is for you. Imagine what it's like for people who may have limited sensory capabilities or limited physical abilities. It's so much harder. So the image on the bottom left is an individual who's blind and is using a touchscreen mobile phone, right? And so the way they use mobile phones is largely through auditory. They swipe through, and every app that's on the phone is read aloud. So it'll go email, weather, calendar, and they swipe through. They learn through audio. They interact through audio. But touchscreens are so visual, right? That is so hard. Or the student, the kiddo on the right, who has a physical mobility. A regular swing, which seems like something so low tech, it doesn't work in this case. Right? And this is why it's so hard for people and technology, low tech or high tech. It's so hard to get along well, right? Because successful transformation isn't about technology at all. It's about people, right? People of all abilities, all interests. It's about people of all ages, right? And that's what makes this thing so hard to do. So in the Chrome Lab, that's what we're really interested in, is how do we design technologies that can better serve all people, okay? And to do this, you have to look and learn from all people. So a big emphasis in what we do in my lab is focused on working with people of various disabilities and various abilities. And we learn from them. And we use what we learned to better the design of technologies for everyone. The interesting thing about technology is that we learn to live with it. And we learn to work with it, even if it doesn't work that well for us. That's called a suboptimal equilibrium. And we operate there, right? And so the purpose of designing inclusively, or what we call universal design, is to raise that so that we don't feel like, well, I'm doing this because it works this way, but it's really not my favorite, right? And we want to be able to raise that bar for everyone. But the hard thing with technology is it's just like clothes. It doesn't fit. One size doesn't fit all, right? So then what we end up doing is making adaptations. And today we're going to talk about different adaptations and ways to make technology more accessible. So we're going to run through a couple of projects that are going on in the Chrome Lab. On the left-hand side, we're going to talk about projects that directly involve people with disabilities. And then we're going to talk about how all of this interplays into designing technologies for all people. Okay? So on the one hand, we learn from people of all abilities, and we use what we learn to better design technologies. Does that make sense? So we're going to talk about that process. So we're going to start here. Does anybody know what this is? Besides a black circle? What is it? It kind of looks like an Alexa. It's a hockey puck. Let me show you what it does. But first we're going to watch a video. So I just want you to watch and notice, make observations about what's going on. All right, we're going to stop there. Anybody notice anything unusual or different or the same compared to what you see when you're watching hockey on TV? What do you notice? The puck clanks. It's bigger than normal. Anything else? There's a whole lot of talking going on. Anybody know why? It's blind hockey. These are people who are legally blind who are playing hockey. Now I got to figure out how to get past this. There we go. So we talked about what's different. And the reason it's different is because it needs to be. A traditional small little puck doesn't work, right? The only way hockey works with that traditional small little puck is if you can see it. And blind people can't see it, right? So instead we have this larger puck. And what's inside of this larger puck are 8 ball bearings. And that's the rattling that you heard, right? And so the way they localize and follow this puck is by listening to it rattle. It's pretty incredible. Did you see how they were moving? I mean, professional blind ice hockey players move really, really fast. It's quite incredible. But even with this kind of puck, what challenges might exist? Right? Well, okay, so as the puck's moving, it's making sound, right? But when it stops, there's no feedback. They have no clue where the puck is when it stops, right? And that's why you hear all of the people talking to one another and trying to localize where they are, where everyone else is, and where the puck is. Not to mention it gets really, really dented up because this thing is really like a can, right? It's a can with it's a big glorified baby rattle, okay? So in the Chrome Lab, we're working on the next generation of what this hockey puck for the blind might look like. And I'll go ahead and pass this around. You can play with it. You can't break it. The lid just screws out. But this is a little bit of an older version, but we'll pass it around. You can look inside. The challenge with doing this is, so we want to develop an electronic puck because an electronic puck can provide audio at any time, right? Even if it stops moving. But, well, electronics that have to go inside of something that's getting hit around and on the ice, mixed with water on occasion, that's hard, right? But the other interesting thing with this puck is really, what sound should it make? If you've heard of beep ball, that's baseball for blind individuals. And the baseball beeps. It goes beep, 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 and it does that the entire game. Right? Which sounds awful, and it kind of is. Right? But it's even worse in hockey, because hockey's indoors, and it's in a rink, and all of a sudden the beeping starts bouncing everywhere, and nobody knows where the actual beep is. Right? So there's been other hockey pucks that have beeped, and that doesn't work. So something that we're trying now is a white noise puck. This is what it sounds like. Doesn't sound awesome to us, but the point is that what we're trying to do is simply amplify the sounds of the normal game, right? When the hockey puck slides on the ice, it kind of sounds like that. And what we're trying to achieve is, can we just take that and amplify it? Provide them as real of an experience as it normally would be, but in a modality that they can work with. Make sense? And this is done in connection with the St. Louis Blues Blind Hockey Club. I don't know if you knew that, but the St. Louis Blues have a blind hockey club. And so that white noise idea came from them. Super fun. What's the point of this project? Even something as simple as a hockey puck can and should be made better, because even that doesn't serve all people. Let's take a look at another project. So this project is focused on making educational content accessible to students with visual impairments and blindness. So I want you to remember or to think about learning math or science. What do you think about? What are things that pop in your head? Struggle. Equations. Symbols. Maybe diagrams, right? Maybe something awful like this, which hopefully doesn't happen anymore, right? But we think of graphs, we think of charts, we think of diagrams. We think of things that are highly, highly visual, right? But this is what math looks like to someone who's blind. Okay? And this is a real problem, because if you think about how our classrooms are going today, it's going to online. It's going to electronic. It's going to digital. So what was already hard is becoming even harder because it's now on a visual screen. So the way they learn math now is they use forms of tangibles or manipulatives. This is called swell paper. When you draw on it, it bubbles up, and then they can feel the raised lines. They use things like corkboards and push pins and rubber bands, right, because you can feel those things. This is an embossed graphic. It's like raised dots. If they come across an image online, it either has to be turned into one of these three forms, or if they're lucky, there's a little auditory description that says, this is a diagram of a flower, right? But think about what that would be like. That would be so hard. A picture's worth 1,000 words, right? Imagine trying to understand this through words. Super hard, right? So what are we working on in the Chrome Lab? We're working on how can we use technologies that are already out there. Touchscreens. We all talked about them at the very beginning. Everyone thinks of touchscreens. How can we use those to make graphical content accessible? And we use sounds and vibrations in touchscreens to do that. So it's things like this. We think about a graphic in a completely different way. We think about it as a multi-sensory experience, right? What if graphics weren't just something we looked at? What if they were something we heard, something we felt, something we interacted with? So this is a pie chart, right, or a bar chart, and we take all the elements of a graphic and we use non-visual means of feedback to represent it. So these bars could make sounds or play vibrations. The lines can do the same thing. We piece apart all of the elements and we represent them in new ways. But the question is, well, would that work? Right? Like, could people do that? And so that's what we study in the lab. We work with individuals with visual impairments, and we said, can they do basic things? Can they follow a line? Right? So this is a line that the red dots make sounds, and the black line vibrates. So whenever their finger's on the black line, it vibrates. They feel it. And when it's off, it doesn't do anything. Right? And we tracked their finger positions all over the screen. And we asked them to redraw what they felt. And it turns out that they can. They can do it really well. Right? So this is a profile of where their finger paths were. And we can see that not only can they follow straight lines, they can follow lines that curve. Now these yellow dots make sounds. We have to give them more information. Right? But if we give them more information, they can even follow curved paths. They can identify shapes. And the question is, well, how do you use vibrations in a meaningful way? How do you experience vibrations on your phone or tablet? What's that? You feel it, right? But in order to really know what it means, you kind of have to look, right? That's not enough. That's not enough for this kind of thing. So we're really digging into, well, what kind of vibrations make the most sense? Which ones would represent dotted lines? Which ones would represent solid lines? And we're really digging into how do we make meaningful vibrations? And then we extend it to something more like the bar charts. Right? So here's a bar chart that's displayed on a touch screen, and this is how it would be rendered for an individual with visual impairments. All of these text labels, the titles and the numbers, that all gets read aloud. Right? So as the finger goes over, it says 80, 82, 84, 86, million acres. Right? The bars, we use sound, and we can adjust the sound by the height. So when we're on this bar, it goes doo, doo, right? So you can match the pitch to the height. And then the little grid lines vibrate, so they can always have some fine tracing tools to get back to where they are. And if anybody wants to try it, you can demo it on the touch screen after the talk. And here's a really cool video of Olivia, her name is Olivia, using the tool. Students really don't get that excited about bar graphs, but this was fun. And now she's following a vibration. 11. So really, really cool. This is an example of how you can use technologies that we already have. This is a Samsung tablet. There's nothing special about this tablet. It's an app on the tablet that we developed. There's no new hardware, right? But this goes to show that we can do so much more with the technology we already have. We're just not using it, right? So there is still so much more to do in education and beyond to make things accessible and equal for all. One more example on this end. This is learning from the deaf-blind population. Has anyone FaceTimed or Skyped or Google Hangout? What do you do when you do that? Call someone up, you see them, you talk back and forth, and you're done, right? So how would you do this if you couldn't see? Potentially. Or maybe somebody helps you like make the call, and then you could hear, right? So you could still hear the audio back and forth, kind of like the old school phone calls, right? Which aren't awful. Well, how would you do this if you couldn't hear? That becomes a lot harder, right? There's sign language. So if I can view someone who's doing sign language and I can sign back, that's an option. Okay, but how would you do this if you couldn't see or hear? We hope, but we don't know. It doesn't exist. And the point of this is that the enjoyments that you and I have to easily call someone up, that doesn't exist for someone who's deaf and blind. Right? And there's a huge movement, and it started in Seattle within the deaf-blind community called the Tactile Movement. And it's so interesting because what this community is doing is they are learning to communicate with one another without interpreters solely through touch, through gestures, through interacting with one another's hands and arms. And they're developing this entire language that's completely touch-based. And they can do it with two people, they can do it in groups. And it's fascinating to see how they can communicate with one another solely through touch. What we want to do is mimic this remotely so that they do have a way to communicate with one another, even if they're not physically present. So we're looking at new ways to develop what we call wearable haptic devices. These are devices that they would wear that provide touch sensations through various different actuation methods. What's the point of this one? There is still so much to do to make common technologies and affordances that we all have and take for granted accessible. Okay? So now let's look at how we take the things that we've learned from these insights and apply them to regular technologies. What if your touch screen could do this?
Critical in that. The real question in today's world is, well, why should touch be important in the way we interface to the digital world? It's an ironic thing that a touch screen is called a touch screen because it knows when you touch it, you have no sense of it at all. And we're just used to that. Canvas came out of university.
Move it up here.
Company that's really, I think, redefining the way that we interact with the most ubiquitous of human-computer interfaces, the touchscreen. We are making it possible to actually feel things that you may see on a touchscreen or frankly any other touch surface through a technology called surface haptics. This is actually a solid-state technology, meaning there's no moving parts at all. The only thing moving is you, and we're controlling.
So imagine feeling smooth and bumpy.
In a way that really goes far, far beyond what you can do by just making something vibrate.
Right? So what if you could feel things that you can relate to? Sticky, slippery, bumpy, smooth. Feel the material of the jeans you're buying on your touch screen. Right? That's where all of these things, learning from people who know touch at its very core, helps improve technologies for all of us. And we're working on that in my lab. So we're building touch screens that can do basically change the friction of the screen without you even knowing it. And by changing the friction on the screen, we make you perceive sensations like slippery, or sticky, or bumpy, or smooth. And all of a sudden, you can start to feel properties that you can relate to. Right? Vibrations are great. We can do a lot of things with vibrations, but they don't mean anything to us. Right? We don't go around and say, oh, this carpet feels like a vibration. Right? There's nothing intuitive about it. This work is focused on making physical sensations that are intuitive and that we can relate to on flat surfaces. And so we've built the sort of the first prototype that can do both of these things, make it slippery and sticky into one single platform. So that's pretty exciting. This is one of my favorite quotes from a famous professor at Purdue who works in the area of haptics, and that's that today's interaction through almost all of the technologies that we have is mostly built for the eyes. Right? So it's pretty hard, it's really hard to think about or imagine how it could be used any other way because we've adapted to that equilibrium. Right? But once we get beyond that, I don't think we'll ever want to go back to a world where we can only see. And that's heartening for all of us, but especially for those who can't see. All right, 2 more. I talked about remote communication, and I talked about how hard that is for individuals who are deaf and or blind. But in reality, remote communication isn't great for any of us, right? We just talked about it. We sit there and we look at a screen and we say, hi, right? But can you hug them? Nope. Right? Can you interact with them in any way besides looking at your screen? Nope. Right? And so there's a lot still missing from how we interact and communicate remotely. And that's where telerobots rose. They came out of the ashes of people saying, this isn't enough. Right? So the idea of a telerobot is that it gives a person greater presence than a tablet or a screen does. Right? Because now I have the ability to sit at my computer and I can drive around and my head shows up on the screen. So somehow people feel like I'm there more. Right? So I can be sitting in Boston and attend the meeting in San Francisco, and I'm more than just a screen. But even telerobots struggle right now because most people see them as Skype on wheels. Right? And they come at a very hefty price tag. So I'll just Skype. Right? But the question is, well, is this a space where we need touch? Right? Because that's really the value, right? It's fun for me to sit here and talk to you because we can see one another and you can see my arms move and you can see my crazy hand gestures, right? Which somehow makes us connected more than if we just saw each other's faces. Okay? And so what we're working on in the Chrome Lab is, can we augment telerobots with more touch capabilities? So we've added a manipulator to the telerobot, and this manipulator can map your remote movements. So if I'm sitting by the computer here and I go like this, the robot waves. And if I say, take a look over there, the robot points. Boom, right? Or if you want to say, hey, you know, that was really great, nice work, thumbs up. Okay? Or if we're really professional about it and we want to shake hands, the telerobot can even do that. Right? But the point is that when we are physically present with one another and we shake hands or we fist bump or we high five, we feel more connected. And none of that is possible right now with remote communication tools that we have. The hand is pretty super cool. It has very human-like movements. It sounds a little wonky yet, but you can see that it can move all 5 fingers, right? And it can move them in different configurations. Right, so we can do points. And what's really cool is we're learning about the forces that are involved in, for example, handshakes. So if you look in this video, we're basically recording all of the forces that exist on the fingers and the palms everywhere so that we can understand and teach the robot, this is how humans like to shake hands. Right? This is how humans like to do high fives. And it can even adapt so that if yours is different than mine, it learns. And then we're going one step further and saying, well, what about the person sitting behind the computer? They want to feel that too, right? So we're developing these wearable gloves that can provide feedback back to the remote user so that you can also take part in the handshake. What's the catch here? Touch feedback connects us in so many ways, right? And it's incredibly meaningful. But if you think about a lot of the technologies that exist right now, touch feedback's nearly non-existent. So there's much to be done. And this extends beyond consumer technologies. This extends beyond education. This extends beyond entertainment. There are many applications where individuals are sensory deficient, not because they physically are, but because of the situation that they're working in. Neurosurgery is a perfect example. In many ways, surgeons are often blind because we've moved to very minimally invasive, small form factor treatment procedures, right? Which means that they're relying on imaging and other techniques, but they can't actually see what they're doing. So in this particular procedure, which is a procedure for treating glioblastomas, this is in collaboration with Washington University in St. Louis. It's a procedure called LITT, stands for Laser Interstitial Thermal Therapy. And what this is a minimally invasive way to treat brain tumors. Essentially, this is a straight probe. It has a laser tip on the end. And when you put the probe in through to the center of the tumor, it cooks the tumor from the inside out. It heats it up, and it kills the tumor tissue. It's really, really a cool procedure. Problem is this. It's a straight tool. It's flexible, but it's straight. And these tumors are never nice geometries, right? So what ends up happening is they can't ever get it all, and they can't sit there and try to move things around because it's a straight probe, right? And so what we're developing in my lab is something that gives them more abilities and more vision. It's something that can curve the probe for them through the same hole that they're already in. And here's a video of that working. So this red blob is the mock tumor, right? And you're going to see an insertion coming in right through here. And you're going to see it curve down into the tumor. And then what you see is this backbone is moving out, but there's still a port in place. So, and this port is along a specified curved trajectory, right? So that straight probe that they initially had is flexible, it's just not steerable. And we've now provided it a way, here comes the probe, we've provided a way to be steered to a new location, right? So here comes the probe in, it's going to follow through this curved port, and it's going to land right into the tumor. So medicine, along with many other applications, is lacking true touch technologies, right? And this is critical because even when we're in different scenarios or different instances where for a moment we might be blinded or we might not have a certain sensory accessible, we need all of the input we can get. And we need to present information through multiple senses as much as we can. So I've taken you through a little bit of a journey, right, where we talked about how we can learn from people of all abilities and how we can use that to better design new technologies for all. And I want you to remember that the most important thing in designing new technologies is that people need to be at the heart of it, right? And this is a wonderful, you might have seen this is a Super Bowl ad, but this is a wonderful story of how Microsoft did just that with a gaming controller.
My name is Grover.
Sean.
My name is Ian.
I'm Taylor.
My name is Owen, and I am 9.5 years old.
I only have one. And yeah.
I love video games, my friends, my family, and again video games.
Whenever I play, it makes me feel happy.
The fun that you get to have with connecting with your friends.
Do you make your own rules?
It's his way of interacting with his friends when he can't physically otherwise do it.
When I'm playing with a regular controller, there's some things that
Don't work for me.
it's difficult for me to use both joysticks. and the D-pad at the exact same time.
And it just slowed me down a bunch more while other people were like,
She's never had the freedom to play at the level she knows she could.
I never thought it was unfair. I just thought, hey, this is the way it is and it's not going to change.
What I like about the adaptive controller is that now everyone can play.
I don't even have to look at the controller, just be like looking at the screen like, hey, yep.
You never want your kid to feel like an outsider or an other.
One of the biggest fears early on is, how will Owen be viewed by the other kids?
He's not different when he plays.
It's a little challenging, but that's the whole point of gaming.
I can hit the buttons just as fast as they can.
And I think I can crush my friends.
No matter how your body is or how fast you are, you can play. It's a really good thing to have in this world.
When everybody plays, we all win, right? And so if there's anything you take away from this talk, I hope it's that how we get people and technology to get along is by ensuring that we design technologies where everyone can play. And with that, I will stop talking. I'd like to thank my family. These are my 3 boys and my husband, my husband's staying home with my 3 boys so I can come here and talk, and that in and of itself is a huge endeavor. This is the Chrome Lab. This is full of people who are innovative, creative thinkers and who are really good people. And they're people-centric, and they're at the heart of all of the cool technologies that we're developing. So with that, I'll stop. We've got a couple of demos if anybody wants to come. This isn't a tele-robot. Those are a little big, but this is a social robot. We've got the touch screen. If anybody wants to come up and see things, you're welcome to, but I'll take questions first.
Is your lab purely research, or are you working with industries and trying to develop solutions?
It's both. It's both. So there's a significant component of it is research, where we're looking at fundamental research questions. But like the hockey puck project is sponsored by Lighthouse for the Blind. The steerable port project is sponsored by Medtronic. I have my own startup, which is an outgrowth of research from the lab. So it's very translational by its nature.
In what ways can the general public help out?
Yeah, I mean, it's a great question. So, well, there's a couple. So one is to never be afraid to point out when things aren't working, right? And to do so to people like myself. Say, hey, like I saw this doesn't work. It would be much better if it did this. The other is to practice inclusion, even in the social context, right? So there's all kinds of other cool videos like the Microsoft one that shows where kids with disabilities feel like they're isolated. Socially, in almost, gaming, lots of different ways. So include people. Include people and be willing to learn from them. And then I'd say the third thing would be, this is from a more research standpoint, but we run user studies all the time. Because the way we learn is by learning from you. So don't be afraid to take part in all of those things when they're like, hey, we have a research study, we're looking for people who have. That's really a great way for us to learn. What else? Yeah.
Touch screens, nothing but polished glass, and I mean, you use keyboards and,
Mm-hmm.
use dials,
Yep.
Tuners, and
Yep.
the approach to tactile, tactile touch.
Yep.
I mean, most of that, this stuff that we're bringing forward is it's a totally different interface.
It's completely different.
And so I mean, your sense of tuner or listening, or your senses are basically being deceived,
Right.
induced. And so I mean, a lot of this stuff is like you're just obsoleting what we've adapted to.
Sure. And I mean, it's, cars used to have the knobs that you'd turn, right? The volume knobs, and now it's like you have this 8.9-inch touchscreen, right? It's the way it's moved, right? And so now the question is, how do we bring those sensations back, right? Because it's really hard. I mean, it's hard to be driving and to try to turn the volume up on a touchscreen on a car, right? I use the things on my steering wheel because it's easier. Yeah.
So what you reviewed tonight in terms of what your lab's been working on too,
Yep.
Has been, technological interface said, you know, the gaps closing. All the innovations that you've gone through tonight, though external, that is, you know, tactile and so
Sure.
forth, that somebody who doesn't have the ability can obtain the ability
Sure.
to, but it's external to the human.
Sure.
Do you do anything, I think the closest thing that came to what I'm talking about in terms of a merging
Yep.
human and machine would be the cybernetics
Yep.
in the arm and in the playing the piano at the beginning.
Yep.
Do you guys also work in that realm as well?
I think a little bit. I mean, so we're not like a prosthetics lab. We don't do that kind of thing. But some of the stuff that we're finding out and we're learning, I think feeds into what those technologies could be. Yeah.
I remember listening to a presentation from an MIT innovation lab in the early to mid 90s, and they mentioned they had just invented this thing, but they didn't know what to do with it. It was called electronic ink. And they said, we're not sure how we're going to be used. Of course, it's the basis of all e-readers.
Sure.
So that you have the screen that sunlight will not bleach it out.
Yep.
You can read it like a book. Well, I'm wondering if anybody is working on, like the gentleman said, touchscreens are just out of class. That a screen that was made of some sort of material that would dynamically change.
Oh, yeah.
Create bumps and create not just vibrations and stuff
Yep.
like that, but the surface would actually
Yes.
morph around, and you could do, I would think the complexity of what you're trying to do would ramp up several thousand.
Yes, there are. There's several what we'd call like deformable surfaces. And you're even seeing some of these come out with like foldable phones, right? That's the first step. But certainly there's what we would call sort of refreshable displays where things can bubble up. They use microfluidics to do that. So there's tons of little tiny channels that run underneath the screen, and then things can bubble up or come down based on it. There's things we call like shape shift, where certain portions of the screen will raise and lower, kind of like the old refreshable pin arrays. Those are certainly under development. I'd say their pipeline in terms of when we would see something like that is quite a bit longer. And there's several hardware hurdles that have to be overcome. But yes, absolutely. The robot's looking at me.
It occurs to me that VR would be a great, in conjunction with
Yep.
virtual presence device. I mean, you reach out and you feel warmth, or you reach
Yep.
out and you feel something. VR would be that'd be really something.
Yeah, and to some extent, even with the telerobot project, we're moving into that because we use the HTC Vive in connection with the wearable gloves. So, yep, absolutely. Yeah.
I've always felt like TV and videos were always a real challenge for people that were blind. Are you working with that in your lab, or what do you feel about advances in that area?
Yeah, so that's a really good question. So a lot of what I talked about was static content from the standpoint of it's a graphic, it isn't going to change, right? So what's done, there's a lot to be done with videos and things that are dynamic or change over time. We're just getting to the point where we're looking at like simulations and animations, and then the next step would be video. So that's a couple of steps away. It's a much harder challenge. Right now what's done is a lot of captioning. But yeah, there's lots of work to be done there. Yeah, I don't know who was first. Go ahead.
If somebody was interested in doing this kind of thing, what sort of things should they study?
Oh, yeah, it's a great question. So I was an engineer by training. I found that to be very conducive for the kind of work that I'm doing. I'm a mechanical engineer. One of the things that I love is that most of the time when people see my talk, they don't think mechanical engineer. And so I have this underlying agenda to make sure that people know that mechanical engineering can mean a lot of different things, and this is one of them. There's a heavy human component. So I have students with backgrounds in psychology in my lab. I have students with backgrounds in biomedical engineering in my lab, electrical engineering. There's a large engineering component for sure, but the human element is very important. Yeah.
Just an observation. I think what you're doing is great.
Thanks.
Great work. I don't mean to be critical, but
oh, it's fine.
It would seem to me that working with touchscreens may
Sure.
thought-driven.
Sure.
And eventually, if you could get to where that little blind girl who was feeling the touch,
Sure.
where the information is just projected straight into her brain.
Sure.
I mean, for people with hearing loss and visual losses, the problem, if their dysfunction is based upon the outer element, the
Sure.
ear or the eye, and the areas of the brain aren't really affected, then they would see it
Sure.
directly by electronic means going in.
Sure.
And so it seems to me like some of the cutting edge research on the interaction of humans and machines is direct thought, kind of what they did in the Matrix with the guy who learned jujitsu in 30 seconds, you know.
Sure.
It's actually demonstrated that in the lab, although they've done it with one word.
Yeah.
So if it goes in that direction, I'm guessing that future technologies, machines are going to be more, instead of being touch related or visual, like, you know, talking into something, talking to your computer, it's going to be, you're just going to think it directly.
Potentially, I think that's a fair ways off, and I think we can do a lot more with what we already have.
Right.
So I think some of the things that I'm working on are much more immediate solutions than those. But yeah, I think, you know, the divide is lowering. You know, whether or not we all end up sort of networked and connected, I think is an open question. Because there's a lot of, I don't think the kinds of work that I'm doing has the ethics and some of the concerns that has. So absolutely, that's an interesting area. And I think some of even the things that we're learning about now will feed into that. But I think that timeline looks a lot longer. That horizon is a bit longer. What else? Yeah, that's a good question too. I was a biology major when I started college. Was thinking about going to med school or maybe PT school, then decided I didn't want to be in school that long. So switched over to mechanical engineering, then went and got my Ph.D. anyway. While I was in my Ph.D., I did a lot with medical robotics, but I was also working in the local Nashville public school system, and I had met 2 blind students. And one of the blind students said, "Oh, you're an engineer, that's awesome." And then she said, "I'll never be an engineer, I'm blind." And I said, "Why do you say that?" And she said, "Oh my God, math is awful." And so I started learning about why math was awful. And I'm like, "You're right, it's awful. And we could do a lot better." And so I had switched over to that kind of being the core focus of my work, and I've been there ever since. Yeah?
I'm a teacher, and I had a high school teacher, and I had a student who was a great problem solver, who was, everything about him said engineer, and that's all he wanted to do.
Yep.
He was blind.
Yep.
And he could not make it through school, and he ended up taking his own life because
Yeah.
that's all he wanted to do.
Yeah.
And school got in his way.
Yeah. I mean, like, we have some huge hurdles right now that I'm hoping this research addresses, which is, I guess, another point to your question of, as much as I love the ideas of what's to come, we've got some issues we need to work out right now with the technologies that we have. Yeah.
Beard, no beard.
Yeah.
Feeling touchscreen, like what? Like, it looked like there was some sort of like voltage underneath the screen.
Yeah.
How is it changing the friction?
It's a good question. Let me see if I can just go back. Not too far. So the way it works is like this. So there's a standard sort of force or friction coefficient that exists between your finger and the normal glass surface. Okay, so if we want to make that slippery, we use what's called ultrasonic friction modulation. And essentially what happens is we vibrate the screen so fast you can't even see it. It's at ultrasonic frequencies. But when we do that, there's this thin film of air that's created between your finger pad and the screen, and you perceive that as slippery. And when we stop doing that, then it feels sticky. And if we use electrostatics, which is sort of electrovibration, we can increase the voltage between your finger and the screen surface, and that makes it feel even stickier. So by going back and forth between those 2 paradigms, you can really create sensations where things feel sticky and slippery on the screen. Yeah, it's a good question. Yeah.
I know a little bit about polished glass, but I mean, it's almost like a piece of sandpaper. I mean, big rocks and small rocks, and you just glue to a piece of paper. I mean, that's the idea of a
Yeah.
piece of glass, essentially.
Yeah.
It's just a matter of density and refinement and
That's right.
most of it has to do with density.
Yeah, we're not changing the actual glass at all. It always stays the same. We're just changing the way that we move it or the way that your finger interacts with it. Yeah.
So is this like the simulated textures, are they kind of like the vibrating graphs and you just put them on the kind of technology that we already have?
Yeah, so that's a great question. So there are no mechanical components. The screens that you're carrying around don't have these capabilities. It's not that hard to add this. There's no extra components, but it's different. So the screens that you have right now couldn't do this. But I would say this is the next thing that will be coming out. It's very, very close to being able to be, there's no components that make it bigger, that make it heavier, and it feels different than vibrations. So then all of these questions get raised about, well, could you have all of them, right? Could you have vibrations and this, and what would that look like? Okay, sure. Yeah, if anyone wants to come up, you're just welcome to play with it.
And also feel free to get some snacks on your way out. Thanks again for coming, and sign up for Summer Reading Club.
Great.